Hi there, my name is Erik Höglund and I will present to you the world of planetary gears, which is a part of this course in machine elements. So if you're all ready, then we start off. Now my presentation will be given in 4 parts, and the first part is an introduction to planetary gears where you will see what they look like and what type of terminology we are using when it comes to planetary gears. So in this slide, for example, you can see that you have a number of gear wheels. This one, which is called the planetary gear. You have this one, the sun gear, and here you also have a gear, an external sun gear. So this is the basic idea of a planetary gear, but we'll go through them one by one. Here you can also see another type of planetary gear, which is rather similar in design, but you can see there are more planetary wheels than on the previous slide. You can also see that each planetary wheel is mounted on a shaft, and in between there is a bearing, so that means that this planetary wheel can rotate relative to this shaft. And the shafts in turn are connected so they all can rotate with the same angular speed around the center here. Inside here you have another sun wheel, and the same goes for out here you have a sun wheel. You can see they are quite big, these type of gears, which means that you don't want to make any mistakes when you do the calculations for such a gear. This is also from a planetary gear from a wind power mill, and here you can see that you have herringbone type of gears. You can also see that it's quite impressive in size, this one. Now all of them are not this large planetary gears, but you can also find small planetary gears. For example, on the rear hub of your bicycle there are in many cases planetary wheels built in, which makes you able to shift gear as you go bicycling. Finally, this slide also shows you a type of planetary gear which is called a differential, and this differential distributes the torque and speed to the outgoing shafts of a front wheel drive car. In this case it's a SAAB. So you see that they can come in different size, different designs. You might think that the planetary gears are quite a new invention, but on the contrary, they have been around for more than 200 years. And the first one who got a patent on planetary gears was James Watt. And today you find many applications, especially in vehicles. We have automotive cars, for example, with an automatic gear shift. There are some obvious advantages. It's very compact. That means that you can have a large power throughput in a relatively small gearbox. The shafts, the in and outgoing shafts, are concentric, which means that it will also make the gearbox to be more compact. You can shift gears without disconnecting from the engine, which is a great advantage if you compare it to ordinary cars where you have a manual gear shift. Of course, there are some disadvantages too. In the design, it comes to a lot of precision manufacturing, which of course also makes this type of gearbox relatively expensive compared to more conventional gearboxes. 3 and 4 wheel type planetary gears. Well, these are the major what you come across most of the times. This is a 3 wheel type, and you may think, why do you call it 3 wheel? Because you have a number of wheels here, but if you have here you have an internal sun gear, an external sun gear, and then you have a number of planetary gears, in this case 5, but they are all similar, as that means that you consider these as being one type of gear wheel. So that means you have 1, 2, 3 types of gear wheels. That's why it's called a 3 wheel type. Now if you compare to this, here you also have internal sun wheel and an external sun wheel. But if you look at the planetary wheel, you see that it has two gear races. One is here, the other one is here. So that means that you have 1, 2, 3, 4 gear races. So this is a 4-wheel type planetary gear. If you draw a sketch of planetary gears, they will very often look like this. This is a 3-wheel gear. We have the inner sun wheel, the outer sun wheel, and the planetary gear. Planetary wheel. And you may have a number of these, but in this sketch you only draw one of them as to explain the design of it. If you then turn to a 4-wheel gear, you see that you have one sun gear, another sun gear. In this case, they are both with their gears on the outside. Here you have the planetary wheel with one gear race here and another race here. So that means you have 1, 2, 3, 4 wheels. This differential is also a fascinating planetary gear, but that's not really within the scope of the course. But of course, if you like, you can find a number of video clips, for example, on YouTube describing how this works. Now, if we concentrate on the 3-wheel gear, we can see the terminology here. You have the inner sun wheel, which is indicated with a digit 2, the number of cogs, and the angular speed. If you go to the outer sun wheel, you have also here the number of cogs and the angular speed. Looking at the planetary wheel, then, you can see that, as I pointed out previously, it can rotate around its own center like this, because there is a bearing between the wheel and the shaft, and at the same time the center of this planetary wheel can move in a circular motion like this with the speed then omega 1. The gear wheel is normally also indicated with a letter, in this case A, that goes for both the number of cogs and the angular speed. This is also a similar sketch, but here you can find it in a little. It's not a picture. It's a sketch of it. But you can essentially find the same things here. You indicate the planet carrier shaft with the index 1. You indicate the sun wheel shafts with the index 2 and 3, and you index the planetary wheel, in this case with the index A. You can also see another thing, that we apply the angular speed, these 4 angular speeds, all drawn in the same direction. So that means that this is defined as the positive direction. And in case some of the wheels will start rotating in another direction, that will be taken care of in the analysis. So this is a very useful concept, that when you start your analysis, you always adopt a positive direction. So, what have we concluded so far? Well, you have a basic design, including a number of planet wheels, which are connected then to a planet carrier shaft. And the planet carrier shaft rotates. That means also that the center of the planetary wheel will rotate in a circular motion. You have a number of sun wheels and also a number of sun wheel shafts. And in the previous case, you could see that we have 2 sun wheels. And this is also to repeat what I said about the indexes. 1 refers to the planet carrier shaft, 2, 3, etc. to the different sun wheels, and A, B, C, etc. to the different planet wheels. Now, to recall what is typical for an ordinary spur gear, we can look at this slide. Here you have a driving wheel and a driven wheel, and you also apply a positive direction for both the angular speed and the torque on the driving wheel as well as on the outgoing wheel, or the driven wheel. And as you may also recall, that if you look at the speed ratio, that will be the same as the ratio between the gear teeth, and what you also see that you have a minus sign here, indicating that the wheels will rotate in opposite direction. Regarding the torque, you see that the ratio of the torques will be equal to the ratio of the number of gears on each gear wheel. And if you then look at the total power throughput, you see that we have no losses here, we have no bearings, we have no losses in the gear mesh. So that means that this is a loss-free, idealized situation. Of course, then the power ratio will say that the efficiency is 1. And now you may ask, why do we have a minus sign here? Well, that simply comes from the opposite direction of the rotational speeds, because you multiply the torque with the angular speed, and that's why it's resulting in a minus sign. If you look at an internal spur gear, we have a very similar situation. We have a driving wheel, a driven wheel. We apply this assumed positive direction in both cases. And if you look at the speed ratio, you can see that it's positive because they both rotate in the same direction. Whereas the torque ratio has a minus sign, meaning that the torques will be in different or opposite direction. And if you look at the power throughput, in this case we don't have any losses, so that means that the power output or the efficiency will be -1, and the minus sign of course comes from the torque ratio. So this concludes my first presentation, and in the next section we will start looking at the analysis of planetary gears. And the analysis can be split up in 5 different steps. It's the analysis of the rotational speeds, so the angular speeds. It's the analysis of the torques without losses. We look at the power flow in the gear, and then we include the losses in the torque analysis. And finally, we're able to calculate the total efficiency. Okay, so that concludes part 1, and the next part will then deal with the analysis of the angular speeds. So, that concludes the first part of the presentation, and I hope you follow me along to the next part. We will look at the analysis of the angular speeds in the gearbox. Thanks for now.